Hey everyone, welcome back. In the last video, we covered energy, which is the capacity for performing work. And we also covered the two types of energy, potential energy and kinetic energy. In this video, we'll go into a deeper level, exploring further on this concept in the terms of force, work, power, and torque. So with that, let's start with force. What is force? Force is defined as the intensity of an impetus or the intensity of an input. The word impetus means the energy with which a body moves. So force is essentially the intensity of energy. It is energy that can influence an object by causing it to change its direction or speed of motion. Force can also be described as a push or a pull that can cause an object with mass to accelerate or move from a state of rest. This can be due to magnetism, gravity, or anything that might cause a mass to accelerate. Speaking of acceleration, force is equal to mass times acceleration, or F equal m times A. Because force is equal to mass times acceleration, it means force has both magnitude and direction, making it a vector quantity. Now that we have a basic understanding of force, let's go through some practical examples to increase our understanding further. I'll have examples throughout the video as we discuss each important topic. So for our first example, let's say we have an aircraft with a total weight of 133,446.6 Newton, which is about 30,000 pounds, sitting at the gate ready for pushback. How much force is required by a tug to accelerate the aircraft at 5 meters per second squared? Before we dive into solving this problem, we need to identify some key information. First, we need to refer back to the formula for force, and that formula is F equal m times A. F is what we need to find, but to find F, we need to know m and A. We already know A because it's given to us right here, which is 5 meters per second squared. Now all that's left is finding m, and from there we can solve for F. How do we find m? To find m, or the mass, take the weight of the aircraft, 133,446.6 Newton, divided by 9.8 meters per second squared. Why 9.8? 9.8 is a constant. It's the acceleration of a free-falling object on Earth. It is the numerical value for the acceleration of gravity. With no air resistance, all free-falling objects accelerate at the same rate due to gravity regardless of differences in mass. In this example, if we had engine off and no air resistance, this aircraft would be accelerated downward by the force of gravity 9.8 meters second squared. In the imperial system, this value would be 32.2 feet per second squared. So in summary, weight is equal to mass times the acceleration of gravity. So therefore, mass is equal to weight divided by the acceleration of gravity. So basically what's happening here is we're taking the weight of the aircraft and dividing by gravity to get mass. So the weight of the aircraft divided by 9.8 meters per second squared will give us a mass of 13,617 kilograms in metric, or 933.1 slug in imperial units. Mass is always in kilogram or slug depending on the system of units. Kilogram is the standard unit of mass in metric, and slug is the standard unit of mass in imperial. 1 slug is equal to 14.594 kilogram. The unit of slug is rarely used. Kilogram is the most common and preferred unit out of the two. Now that we have mass and acceleration, let's solve for the final variable, force. So 13,617 kilograms times 5 meters per second squared equals 68,085 Newton in metric, or 15,302.84 pounds in imperial units. This is how much force is required by the tug to accelerate the aircraft at 5 meters per second squared. And now let's move on to work. What is work? Work is a further classification of force. It is the physical measurement of the amount of force required to produce a given amount of movement. This means work is done when a resistance is overcome by a force acting through a measurable distance. If a force is applied to the object and the object does not move, by definition, no work has been done on the object, because work is only accomplished when the object displays some distance against a resistant force. So, in mathematical terms, work is defined as force times distance or displacement, which is force applied over an X amount of distance. Work is measured in terms such as foot-pound and joule. This means that the amount of work done is directly proportional to the force applied and the distance the objects move. We can demonstrate this through two simple examples. First example, how much work is accomplished when a GE CF34-8E engine weighing 2,600 pounds is pushed across a hangar floor, a distance of 160 feet, with a force of 85 pounds. For this problem, we won't go into metric, we'll just focus on the imperial system. We know that work is equal to force times distance, or W equal F times D. So let's simply plug and solve. 85 pounds for force multiplied by 160 feet for distance is equal to 13,600 foot-pounds. So 13,600 foot-pounds of work is accomplished to move this engine 160 feet with 85 pounds of force applied. For the second example, how much work is accomplished when the same engine weighing 2,600 pounds is hoisted up 8 feet? In this example, since the engine is being moved in a vertical direction rather than a horizontal direction, the displacement of force is a little different. So therefore, we'll use the weight of the engine for the applied force. We know that work is equal to force times distance, and it looks like we have all the information we need. So this is a simple plug and solve. Just like the previous example, 2,600 pounds times 8 feet equal 20,800 foot-pounds. So 20,800 foot-pounds of work is accomplished when a 2,600 pound engine is hoisted up 8 feet. In the two simple problems we just did, you can see how work is easily demonstrated. With an applied force plus an X amount of distance or displacement, we get the output of work. We're now starting to get a good understanding of work, so let's define it further by talking about torque and power. Let's first start off with torque. What is torque? Just as a force is a push or pull, torque can be thought of as a twisting or turning force. It's the tendency of a force to rotate an object about an axis, or fulcrum or pivot point. Most often, torque can be commonly mistaken as being the same as work and vice versa. Perhaps a contribution to this could be, in the simplest form, both are equal to force times distance. By this formula, it can be seen where the confusion lies. Let's compare the two and see what sets them apart. The magnitude of torque depends on three variables. 1. The force applied. 2. The length of the lever arm connecting the axis to the point of force application, which pretty much translates to distance. And 3. The angle between the two. From this, we get the following formula for torque. R times F describes the vector of the torque. R times F multiplied sine of theta describes how large the force is. It's the magnitude of the vector force. If you notice, the vector force formula for torque is very much the same formula for work. Where work is F times D, torque is R times F. This means both D and R are interchangeable because they both describe length. So then, what's the difference between the two? While work is a force acting through a distance like we defined earlier, torque is a force acting along a distance. Make sense? No? Okay, perhaps it will make more sense through the following example. Let's say we've been assigned to replace an aircraft main landing gear wheel tie assembly. After getting set up and removing everything we need to remove per the aircraft maintenance manual, we finally get to the final nut. To remove the axle nut and then the tire assembly, we first have to break the torque on the nut with a breaker bar. When we do this, there are two possible outcomes. Outcome 1, when we apply force to the breaker bar, the axle nut turns. Or outcome 2, when we apply force to the breaker bar, the axle nut does not turn. With these two possible outcomes, work is achieved on the axle nut only in outcome 1, but not in outcome 2. Why is that? Remember, work is force applied over distance. This means work is only achieved when there is a measurable distance. Since the nut did not turn in outcome 1, there was no measurable distance, thus no work performed. However, torque does not abide by this rule. In the example, even though work is only achieved in outcome 1, torque is achieved in both outcome 1 and outcome 2. That's because torque is achieved even if no work has been accomplished. To further clarify how work and torque are different, we can look at how their units are expressed in the imperial system. In the imperial system, the unit for work is expressed as foot-pound or foot-pound force and inch-pound or inch-pound force. Most people will argue that this is also the unit expression for torque, and you've probably heard people express torque this way, but that's the incorrect method. Most of this has to do with how torque wrenches are marked. Most torque wrenches found in the US are often marked as foot-pound or inch-pound when measuring torque, which is 100% incorrect. In the imperial system, torque is properly expressed as pound-foot and pound-force inch, which is simply pound-inch. In the metric system, there is no confusion on this. Work is expressed as joule and torque is expressed as Newton meter, and torque wrenches reflect this. You will never see a torque wrench that says meter Newton. So with that, let's move on to power. We know that work is equal to force times distance, but what if we added a third variable to this equation, and this variable being time? What would this give us? This would give us what is known as power. By definition, power is work done over time. It is the time rate of doing work. So we could say that power is equal to force times distance divided by time, or work over time. Time in this equation has a direct correlation to power and work. Decreasing time will increase power output, and increasing time will decrease power output, and vice versa. Theoretically, more power means less time it takes to accomplish work, and less power means the more time it takes to accomplish work. When expressing power, it can be expressed in multiple ways. Some of these common ways are foot-pounds per minute, foot-pound per second, and inch-pound per minute or second. Foot-pound and inch-pound are used for the units of power because, remember, power is essentially the definition of work, but with time added. In metric, power is joules per minute or second. Another common way to express power, especially when referring to internal combustion engine, is horsepower. Horsepower is probably a term you've heard countless times and very much familiar with. But for the purpose of this video, I'm going to briefly go over what it is, but first we gotta learn some brief history. Many years ago, a Scottish inventor by the name James Watt, who built some of the first engine, wanted to know how many horses the performance of a steam engine was equal to. He figured out that the average horse could lift 550 pounds of weight 1 foot off the ground in 1 second. So he made that equal 1 horsepower, and thus the term horsepower was created. From there, the following conclusion was made. 1 horsepower is equal to 550 foot-pounds per second, 33,000 foot-pounds per minute, and 746 watts. The watt is mostly used when dealing with electric motor. So what's the importance of these values and their units? These values are known as constant, and they can come in use when trying to solve for horsepower. What does that mean? Let's first look at the equation for horsepower. The equation used for horsepower is force times distance divided by a constant multiplied by time. A constant being one of these following values. During calculation, based on the units being used, we can substitute in any one of the listed constants to find horsepower. If we wanted to, for easier calculation, we could solve for power first, which is force times distance divided by time, and then take the power value and divide by one of the constant. What is the horsepower needed to horse a 2,600 pound tail mounted engine 15 feet in 1.5 minutes? Before we get started on this problem, let's first identify some key variables. These variables are engine weight, engine height, and time. Engine weight is equal to 2,600 pounds. The height at which the engine would be lifted to is 15 feet. The time it would take to lift the engine 15 feet is 1.5 minutes. Now that we've identified our variables, let's use the formula for horsepower and plug in the given variables. 2,600 pounds will substitute for force, 15 feet will substitute for distance, and 1.5 minutes will substitute for time multiplied by a constant. We are almost ready to solve the equation, but first we are still missing one key information. What constant do we use? We have to decide out of the three constants which one fits the best. The unit of the third variable is the key. Since our third variable is in minutes, we will choose 33,000 foot-pounds per minute as the appropriate constant to use in this equation. Let's plug in this number and then let's multiply and divide. When we do this, the units of foot-pound cancel out, and all we are left with is 0.79 horsepower. And now for the last topic of this video. Let's briefly talk about friction. Whenever work is performed, there's always a resistant force that opposes it or prevents it from happening. This force is known as friction. Friction is defined as opposition to the relative movement between two objects. It is calculated by the formula F equals mu times N, where F is the force of friction, the Greek letter mu, which looks like a U but is not, is the coefficient of friction, and N is the normal force. There are numerous types of friction, but they can all be classified into three kinds: static friction, sliding friction, and rolling friction. As you can see, each friction has their own corresponding formula. The formula are very much identical apart from a few notation. Let's break these notation down. The subscript letter after the letter F represent the type of friction such as static, kinetic, and rolling friction. The subscript letter after the Greek letter mu, which looks like a U, represent the coefficient of the type of friction. The coefficient is not a force, but rather it is used as a value to find the force of friction. And finally, the subscript N after the letter F represent normal force. So now let's define each classification. Let's start with static friction. Imagine you have a box with an X amount of mass you're trying to move. To move the box, you try to slide it across the floor by applying an X amount of force against the box. Your applied force on the box is met by an opposition force that's preventing you from moving the box. This opposition force is what is known as static friction. Static means not moving, so static friction is defined as the force that is required to move one body relative to another when they are at rest. It is also known as starting friction. Let's go back to our box example. Let's say you eventually apply enough force to the box to overcome the static friction, and now the box starts to slide across the floor. Because the box is not in motion, the static friction is converted into what is known as sliding friction, also called kinetic friction. This action creates an inverse relationship between static and sliding. We'll discuss more about this relationship in a few moments, but first, let's define sliding and rolling friction. Sliding friction, also known as kinetic friction, is a contact friction that resists the sliding motion of two objects or an object and a surface. Sliding friction is almost always less than that of static friction. This is why it's easier to move an object once it starts moving rather than to get the object to begin moving from a rest position. And lastly, rolling friction. Rolling friction is the force resisting the motion when an object such as a ball, a tire, or a wheel rolls on a surface. Given the following information, calculate Fs and Fk. To help with our calculation, let's first make a diagram. Let's say we have a box and it has a mass of 25 kilograms. An X amount of force is applied to the box to move it. With the applied force, there is an opposition of friction. This friction is either static or kinetic. The reason being is because static and kinetic friction cannot exist at the same time. It's always one or the other. We know that everything on Earth exerts some amount of downward force, including our example box. This downward force is known as weight, and it equals mass times gravity, or m times g. This downward force is also opposed by an upward force of the same value, known as normal force. Normal force is a contact force that is perpendicular to the surface that an object contacts. Okay, at this point, we've gotten all the information we need. So now we can start solving. Fs is less than or equal to the coefficient of 0.30 times normal force, which is mass of 25 kg multiplied by the force of gravity of 9.8 meters per second squared, which will give us 0.30 times 245, and that equals 73.5 Newton. For kinetic or Fs, we will substitute the coefficient of 0.30 for 0.20 and then multiply by 25 kg times 9.8. So 0.20 times 245 will give us Fk of 49 Newton. So there you have it. Fs is 73.5 Newton and Fk is 49 Newton. It's great that we found Fs and Fk, but what does these numbers mean? For Fs, 73.5 is the resistance provided by the box and the surface it sits on. It means that the correct amount of force must be applied to the box to overcome the resistance for the box to move. If the force applied does not exceed the force of static friction, in this case 73.5 Newton, then there will be no movement on the box. If the force applied exceeds 73.5 Newton, static friction no longer exists because the box is not in motion. This means we now have Fk, or kinetic friction, which will be the value of 49 Newton for this example. As long as we continue applying a force greater than 73.5 Newton to this box, the value of kinetic friction will always be 49 Newton for this example. This is it for this lesson. Thank you for watching. If you found this video helpful, please give it a thumb up and hope to see you next time.